What if the universe is breaking the rules we built to explain it? A Nobel Prize-winning discovery revealed a serious problem with cosmic expansion. Then James Webb found early galaxies that looked too large, too developed, and too soon. Now, scientists are questioning the universe's speed, structure, dark matter, and our place within it. Today, we explore the strange evidence changing how we understand the universe. Before we go any deeper, please take just 1 second to hit like and subscribe to the channel. It's completely free, but it makes a huge difference for us. Now, let's begin. The Standard Model of Cosmology, the greatest intellectual achievement in the history of science, built by thousands of the most brilliant minds across 100 years, may be wrong at its very foundation. Not wrong in the way a minor calculation goes off by a rounding error. Wrong the way a bridge is wrong when its load-bearing pillars are cracked. And the evidence didn't come from speculation. It didn't come from a fringe theory or a dissident physicist typing manifestos at 3 in the morning. It came from the most precise measurements humanity has ever performed. That's what makes this terrifying. In 2019, Nobel Prize winner Adam Rees said something that should have stopped the entire scientific world cold. "There is something really wrong with our universe," he declared, "or with our understanding of it." This was not a blogger, not a contrarian. This was the man who won the Nobel Prize in Physics for discovering that the universe isn't just expanding, it's accelerating outward, faster and faster toward a fate no one fully understands. When that man looks at the data his own team has spent decades refining and says something is wrong, you don't dismiss it. You listen. To understand why this matters, you need to know what we're actually talking about when physicists say the Standard Model of Cosmology. Its formal name is Lambda CDM. Lambda for dark energy, CDM for cold dark matter. Think of it as the GPS of the universe. For 30 years, every astronomer, every cosmologist, every telescope pointed at the sky has been navigating by this map. It tells us how the universe was born, how it grew, how matter clumped together into galaxies, and critically, how fast the whole thing is expanding right now. It's the operating system underneath every astronomical discovery of the modern era. Every observation gets cross-referenced against it. Every anomaly gets measured relative to it. It is, by any reasonable standard, the most tested scientific framework ever constructed. And right now, it is telling two completely different stories at the same time. The problem has a name. It's called the Hubble tension. Dry as a bone on the surface, catastrophic underneath. Here's the core of it. Two completely independent methods of measuring the expansion rate of the universe, methods built on entirely different physics, using entirely different instruments, designed and operated by entirely different teams, keep producing two numbers that cannot be reconciled with each other. One method looks backward in time, reading the oldest light in existence. The other reaches out and measures individual stars across billions of light years. They are both rigorous. They are both verified. And they disagree, not by a little, not within normal experimental uncertainty. They disagree by a gap so consistent and so stubborn that it has now survived more than a decade of attempts to explain it away. The probability that this is random chance, a fluke, a coincidence, a statistical hiccup, is 1 in 100,000. In particle physics, you need a 5 sigma threshold to even claim a discovery. What we have here clears that bar. The disagreement is not noise. It is signal. Real, repeating, unmistakable signal, telling us that something in our map of the universe is either missing or broken. Think about it this way. Imagine you take the two most accurate clocks ever manufactured, calibrated by two completely separate teams of the world's best engineers, synchronized against every available standard. And every single day, without exception, one runs 8 minutes faster than the other. Not sometimes, Not under certain conditions. Always. Every day. Permanently. At some point, you stop asking which clock is wrong and start asking whether your understanding of time itself has a flaw you haven't noticed yet. That's exactly where cosmology is right now. If both measurements are sound and every attempt to find an error has come up empty, then you are left with a question that has no comfortable answer. If the two best tools humanity has ever created to measure the same thing keep returning different results, which one do you trust? Do you trust the one reading the blueprint of the universe as it existed 380,000 years after the Big Bang? Or do you trust the one physically reaching across space and measuring the light of individual stars? You can't trust both, and you cannot afford to dismiss either. This is not a case of one rogue measurement gone wrong. It is not a single telescope with a miscalibrated mirror or a dataset that someone forgot to correct for temperature. This is a systematic contradiction, a deep structural disagreement between the two largest pillars of modern cosmology. One that has only grown sharper as the instruments have grown more powerful. Every time physicists found a potential loophole, they closed it. Every time they suspected a technical error, they checked and found nothing. The tension has persisted for more than a decade. It has survived new data, new telescopes, new analysis techniques, and new generations of researchers who went looking specifically for the mistake and couldn't find it. The crisis is not a glitch. It is a feature of the universe we do not yet understand. But to grasp why this is so catastrophic, you need to understand what these two measurements are actually doing. One gazes into the deepest past the universe has, reading light that is 13.8 billion years old. The other reaches out and physically touches the stars. And they have never, not once, agreed with each other. 13.8 billion years ago, the universe screamed. Not metaphorically, physically. A wall of light and energy so intense it filled every point in existence simultaneously. And that scream is still echoing across the night sky, right now, at this very moment, hiding in a frequency your eyes will never see. It's called the cosmic microwave background, the CMB, and it is the oldest light that still exists anywhere in the universe. To understand what it is, you need to picture the early universe, not as empty space with things in it, but as a single, violent, unbroken ocean of plasma, so hot and dense that light couldn't travel more than a fraction of an inch before being absorbed and re-emitted. For 380,000 years after the Big Bang, the universe was completely opaque. Nothing could escape, nothing could propagate. The entire cosmos was a sealed room with the lights on, but no windows. Then, 380,000 years in, the temperature dropped just enough. Electrons and protons finally slowed down enough to combine into neutral hydrogen atoms. The fog lifted. In an instant, cosmically speaking, the universe became transparent, and all that trapped radiation flooded outward in every direction at once. That moment is what we call the CMB. It is the fingerprint left at the scene of the Big Bang. You weren't there when it happened. Nobody was. But the fingerprint is still there on every surface. And if you know how to read it, you can reconstruct everything that happened. Imagine arriving at a crime scene years after the event. The body is gone, the witnesses are gone, but there's a fingerprint on the wall, perfectly preserved. From that single fingerprint, a forensic expert can tell you the height of the person who left it, their approximate age, which hand they used, how much pressure they were applying. The CMB works the same way. It carries encoded within its subtle temperature variations fluctuations of less than 100,000th of a degree, the complete physical blueprint of the infant universe. Read it correctly, and you can calculate not just what the universe looked like then, but what it should look like now. The Europeans launched a satellite called Planck in 2009. For 4 years, from 2009 to 2013, it stared at the entire sky simultaneously and mapped the CMB with a precision that had never been attempted before. The margin of error was 0.1%. Not 1%, 0.1. The resulting map was the most detailed portrait of the early universe ever produced. A full sky image of the cosmos as it existed nearly 14 billion years ago. Accurate to fractions of a degree in temperature across billions of light years of space. The number that came back was 67.4 kilometers per second per megaparsec. That is the expansion rate of the universe, according to the blueprint, according to the physics baked into light that has been traveling since before our galaxy existed. 67.4. Predictable, stable, perfectly consistent with everything Lambda CDM had ever told us. The universe, read from its oldest surviving signal, was expanding at a measured, elegant pace. The model held. The blueprint matched the theory. Now, it's important to understand what this measurement actually is, because it's not a direct observation the way looking through a telescope is a direct observation. It's a calculation run backward through the physics of the early universe. Think of it like being handed the original architectural drawings for a building you've never visited. You don't need to stand in front of the building to calculate its current height. You read the blueprints. You apply the engineering formulas. You derive the answer from the design itself. That's what the CMB method does. It reads the original specifications of the universe and extrapolates forward to today. This is precisely why scientists trust it so deeply. The CMB has no contact with anything messy. It doesn't pass through dust clouds that might distort it. It doesn't interact with the complex gravitational choreography of modern galaxies. It doesn't care about supernovae or star formation or any of the complicated astrophysics that fills the universe today. It is pristine. It is ancient. It is, in the eyes of the CMB camp, the most reliable data in all of cosmology. A direct line to the physics of the universe before anything complicated had a chance to go wrong. Essentially, this is what physicists in the CMB camp are saying. I don't need to look out the window. I have the blueprints from 13.8 billion years ago. And blueprints don't lie. Until, apparently, they do. Because if the blueprint says 67.4 and the building you're standing in front of keeps measuring 73, you have a problem. Either the blueprint has an error nobody caught in 30 years of checking, or the building is doing something no blueprint ever accounted for. Either way, you can no longer simply trust the drawing and call it done. This is the foundation of one side of the argument. Half of cosmology plants its flag in the ancient light, in the frozen moment of 380,000 years after creation, and says the universe expands at 67.4. The math is sound. The physics is verified. The answer is in the design. If you have the original design of something, but the real thing looks completely different when you go and measure it in person, is the problem in the blueprint or in the thing itself? The other half of cosmology doesn't read blueprints at all. They go outside. They climb the building. They press a ruler against every floor, every rung, every star. They can reach across billions of light years of space, and they come back with a different number every single time. And when you actually touch the universe, measuring star by star, galaxy by galaxy, real distance by real distance, the number you get is not 67, it is 73. And that gap is tearing everything apart. There are stars in the universe that pulse like perfect biological clocks. They swell and contract in absolute rhythmic precision, brightening, dimming, brightening again on a cycle so consistent, so mathematically reliable, that you can use them as a ruler stretching across millions of light years of empty space. They don't care how far away they are. They don't care how old the universe is. They just keep ticking. These are Cepheid variable stars. and for over a century, they have been one of astronomy's most powerful tools. The reason they work as distance markers is elegant in its simplicity. A Cepheid's brightness fluctuates on a cycle, and the length of that cycle is directly proportional to its true luminosity, how much light it actually pumps out. This means that if you watch a Cepheid pulsate for a few weeks and clock the period of its variation, you immediately know its absolute brightness. Then you compare that known brightness to how bright it actually appears in your telescope. How faint the signal is by the time it reaches you. The difference tells you exactly how far the light has traveled to get here. It works like a lighthouse. If you know a lighthouse emits exactly a certain number of watts, and you can see how faint it looks from your position, you can calculate your distance from the shore down to a very small margin of error. Cepheids are lighthouses that announce their own wattage with every pulse. But Cepheids alone can only take you so far. Beyond a certain distance, even the most powerful telescopes struggle to resolve individual Cepheids inside dense, distant galaxies. So astronomers built something more ambitious. They constructed the cosmic distance ladder, a chain of overlapping measurement techniques, each one calibrated against the one below it, each one reaching farther than the last. It starts close. At the very bottom of the ladder is our own solar system, measured with radar and laser ranging to extraordinary precision. From there, astronomers use stellar parallax, the tiny apparent shift in a nearby star's position as Earth moves around the Sun, to calibrate distances to the closest stars. From those calibrated nearby stars, they can anchor the Cepheid relationship. From nearby Cepheids, they can reach outward to Cepheids in neighboring galaxies. And once you have Cepheid-anchored distances to those galaxies, you can identify Type 1a supernovae within them. Type 1a supernovae are the next rung up, when a white dwarf star in a binary system pulls enough mass from its companion to push past a very precise mass threshold, 1.4 times the mass of our Sun, known as the Chandrasekhar limit, it detonates. The explosion is so consistent, so physically constrained by that hard mass limit, that every Type 1a supernova releases almost exactly the same amount of energy. 100 billion times the luminosity of the Sun. Always, every time. This makes them what astronomers call standard candles, objects of known absolute brightness that you can see from literally billions of light years away and use to measure the expansion of the universe at cosmological scales. The ladder runs from your own backyard all the way to the edge of the observable universe. Every rung depends on the one below it, and every rung extends the reach of the measurement further. Adam Rees built his career on this ladder after winning the Nobel Prize in 2011 for the discovery of accelerating cosmic expansion. He didn't stop measuring. He led a project called SH0ES, Supernova H0, for the equation of state using the Hubble Space Telescope to measure thousands of Cepheid stars across dozens of galaxies with the most rigorous methodology the field had ever seen. His team checked their work obsessively. They cross-verified every calibration. They ran the analysis multiple ways, and every single time, the number that came back was 73.04 kilometers per second per megaparsec. Where the CMB camp reads blueprints, the distance ladder camp goes to the construction site. You don't derive the height of a building from its architectural plans. You climb it. You put an actual measuring tape on every floor, every stair, every beam. You make direct physical contact with the thing you are measuring. That is what the cosmic distance ladder does. It reaches across billions of light years and physically touches the universe, rung by rung, star by star, explosion by explosion, until a number emerges from the data itself. By 2022, the statistical tension between these two methods had reached 5.0 sigma. In particle physics, 5 sigma is the threshold required to announce a new discovery. When the Higgs boson was confirmed in 2012, it was announced at 5 sigma. That is the bar the entire physics community agreed represents the boundary between probably real and definitely real. In cosmology right now, 5 sigma is not a discovery threshold. It is a crisis threshold. It means the disagreement between 67.4 and 73.04 is so statistically robust, so far beyond what random noise could produce, that it cannot be explained away by measurement uncertainty alone. Something else must be wrong. When two independent measurements, each verified by hundreds of scientists across dozens of institutions on multiple continents, disagree at 5 sigma, what does that say about everything else we thought we knew? Adam Rees won the Nobel Prize for finding that the universe is accelerating its expansion. Then, he kept measuring, more carefully, more precisely, more thoroughly. And what he found was that the universe is also doing something that even he, the man who redrew the map of modern cosmology, cannot explain. There is a word for what happens when being extraordinarily good at your job leads you to a discovery that dismantles your own framework. It is not comfortable, but it is, undeniably, science at its most alive. In 2022, humanity launched a telescope 100 times more powerful than Hubble, with a single ultimate mission: prove that the number 73 was a mistake. What it brought back would satisfy no one. James Webb was not launched to find something new. That is the part the press releases never quite said out loud. Yes, there were the official goals: the first stars, the earliest galaxies, the chemistry of alien atmospheres. All true, all real. But underneath the official mission, running parallel to it like a second current beneath the surface of a river, was something more urgent. In the eyes of many physicists, James Webb had one real assignment: silence the crisis. Go look at the same stars Adam Rees had been measuring for decades, resolve them with a clarity Hubble never had, and come back with a clean answer. The old measurements were wrong. The tension was a ghost. The standard model was safe. We can all go home. That is not what happened. To understand why James Webb was handed this particular assignment, you need to understand the specific accusation that had been leveled at Hubble for years. The accusation had a technical name: the crowding problem, and it was a genuinely plausible escape hatch. When you point Hubble at a Cepheid variable star inside a dense, crowded galaxy core, you are not necessarily looking at one star. You are looking at a pixel, and inside that pixel, crammed together by the limitations of the optics, there might be 2 stars, or 5, or 30. Their light blending together, their signals merging into a single point of brightness that Hubble's instruments cannot pull apart. If that is happening systematically, then every Cepheid measurement Rees and his team ever made could be artificially inflated. The stars would appear brighter than they truly are. Brighter means apparently closer. Closer means the expansion rate calculated from them gets pushed upward. The number 73 would not be a discovery. It would be a contaminated measurement that generations of astronomers failed to catch because they never had an instrument precise enough to see the contamination in the first place. It was a clean, elegant theory, and there were serious physicists who believed it. James Webb's primary mirror spans 6.5 meters, more than 2.5 times the diameter of Hubble's. More critically, it operates in the infrared, which means it sees straight through the dust clouds that scatter and absorb visible light. Dust that fills the crowded central regions of galaxies in enormous quantities. With that combination, larger aperture, infrared sensitivity, extraordinary spatial resolution, Webb could do something Hubble never could. It could stand inside a packed, chaotic galactic center and pick out individual stars the way you might pick individual faces out of a crowd photograph taken from orbit. If the crowding problem was real, Webb would expose it. If Hubble had been fooled, Webb would catch it in the act. In February of 2023, Adam Rees and his collaborators published their findings in the astrophysical journal Letters. They had used James Webb to remeasure the entire Cepheid chain from scratch. Different instrument, different wavelengths, far sharper resolution. The crowding problem, to the extent it existed at all, was now fully visible and fully correctable. The number that came back was 73 kilometers per second per megaparsec. Not approximately 73, not a revised figure that split the difference. 73, identical, unmoved. Utterly indifferent to the most powerful telescope humanity had ever pointed at the sky, the optical error hypothesis was officially dead. The hypothesis of Sai-So Kwanghak, the idea that decades of blurred pixels had manufactured the crisis from nothing, was closed, sealed, and buried. The contradiction was not a technical artifact. It was real. Think about what this means in concrete terms. You hire the world's greatest detective specifically to disprove the evidence against your client. You give them unlimited resources, the best tools in existence, and years to work. The detective comes back, sets the report on the table, and says every piece of evidence is authentic. The case against you is real, every single piece of it. That is what James Webb said to the Standard Model in February of 2023. Wendy Friedman, astronomer at the University of Chicago and one of the most respected voices in this field, did not soften her language. She called this the moment the real crisis began. Not the moment of the crisis's discovery, not its confirmation, its true beginning. Because before Webb, there was always a plausible argument that an instrument was at fault. After Webb, there is no instrument left to blame. There is no technical exit remaining. The disagreement between 67.4 and 73 is not a measurement artifact. It is a property of something the universe, or our model of it, that we do not yet understand. When the last emergency exit closes, where does science go? $10 billion, 25 years of construction, delays, redesigns, near cancellations, and one of the most complex spacecraft deployments in human history. James Webb unfolded its golden mirror 1.5 million kilometers from Earth with a precision measured in nanometers. And its first major contribution to cosmology was the confirmation that we are in deeper trouble than anyone previously thought. That is value for money in the most literal sense possible. But James Webb did not stop there. When it turned its mirrors toward the very first galaxies that ever existed, it found something that did not merely contradict the Standard Model, it came close to tearing it apart entirely. After James Webb closed the first escape route, scientists tried a completely different strategy. Not a refinement, not a more careful version of the same measurement, a total replacement. Strip out the Cepheid variable stars entirely. Discard every assumption the distance ladder had built on their pulsations. Start over from zero, using a completely different class of object, governed by completely different physics, with no shared methodology, no shared instrument, no shared calibration chain with the approach that produced 73. If the Cepheids were somehow systematically wrong in a way Webb couldn't detect, a measurement built on entirely different stellar physics would reveal it. The new number would land closer to 67, the tension would ease, the model would breathe again. Instead, a third number appeared, and it satisfied no one. The replacement method is called TRGB, the tip of the red giant branch. The physics behind it is entirely distinct from Cepheids. When a low-mass star exhausts the hydrogen in its core, it expands into a red giant, growing larger and brighter as helium begins to fuse. This process has a precise physical ceiling, a maximum luminosity the star reaches at a specific moment in its evolution, before helium ignition causes a sudden internal restructuring that drops the brightness sharply. That sealing occurs at almost exactly the same absolute luminosity in every star that reaches it. It is a hard physical limit set by the laws of stellar structure, independent of the star's age, its metallicity, its history. You identify the brightest red giants in a galaxy. Find the sharp cutoff where brightness drops, and that cutoff gives you the absolute brightness of those stars. Compare it to their apparent brightness, and you have a distance. Completely different stars, completely different physical mechanism, completely different everything. Wendy Friedman's team, the Carnegie-Chicago Hubble program, known as CCHP, spent years refining this method. In 2024, they published their result, 69.96 kilometers per second per megaparsec. Not 67.4, not 73, 69.96. A third number, sitting in the middle of the existing argument, too high to validate the CMB and too low to validate the distance ladder, offering resolution to neither camp and new confusion to both. At the same time, gravitational waves were producing their own answers. When two neutron stars spiral into each other and collide, they produce a burst of gravitational waves whose amplitude encodes the physical energy of the merger. Unlike Cepheids or red giants, this method, called standard sirens, requires no calibration against any other astronomical object. It reads distance directly from the geometry of space-time itself, completely independent of every rung on the cosmic distance ladder. Results from various studies have landed somewhere between 68 and 72 kilometers per second per megaparsec, overlapping partially with both camps, confirming neither, and not yet reaching the precision needed to be a decisive arbiter. 3 skilled craftsmen, 3 different rulers, 1 room. The results come back as 67, 70, and 73. Nobody cheated, nobody used a bad tool, nobody made an obvious error, and nobody can explain why. Nobody can blame anyone else. This is the part where something shifts qualitatively. When the Hubble tension was just Cepheids versus CMB, you could still tell a story about one method having a hidden flaw, one rung on the ladder being subtly miscalibrated, one assumption buried deep in the distance chain that nobody had caught. Uncomfortable, but contained. One side is right, one side has an error. Someone will eventually find it. That story no longer fits. If all the rulers appear to be working correctly, but keep returning different answers, could the problem be in the universe itself? When methods built on entirely different stellar physics, measured by entirely different teams, on entirely different instruments, all disagree with each other, the most frightening possibility stops looking like a fringe idea. It begins to look like the only conclusion left standing. The problem is not in any specific tool. It may be in the universe itself. Specifically, in the assumption that has sat beneath all of this, untested and unquestioned for decades. The assumption that the universe is homogeneous, that it looks the same in every direction, from every location, at every scale. That a measurement made from here is equivalent to a measurement made from anywhere. Physicists are in a situation that feels like this. You ask 3 friends how long a film runs. They all watch the same film. They all used good watches. They all give you different answers. At that point, you stop checking the watches. You start questioning time itself. And when you start questioning the foundations, the theorists have no choice but to reach for something no one has ever seen. A form of energy so strange, so brief, so perfectly timed, that it existed for exactly the right number of years after the Big Bang, reshaped the expansion history of the infant universe, and then vanished completely, leaving no direct trace of any kind. To save the standard model without demolishing it, scientists proposed something that sounds like science fiction. A mysterious form of energy that flared into existence right after the Big Bang, lasted for exactly a few 100,000 years, accelerated the universe, and then vanished completely, as though it had never existed at all. This is not dark energy. That distinction matters enormously and gets blurred almost every time this topic reaches a general audience. The dark energy embedded in the Standard Model, the lambda in lambda CDM, is the thing driving the universe's expansion today. The slow, relentless push that will eventually pull every galaxy beyond the horizon of every other galaxy over the next hundreds of billions of years. That dark energy is still here. It is operating right now. It is a permanent fixture of the cosmos as we understand it. Early dark energy is something else entirely, a different animal. It would have existed only in the first chapter of cosmic history, active before the cosmic microwave background was even emitted, operating during the hot, opaque, furious infancy of the universe, and gone before the first atoms fully formed. It does not exist today. It left no ongoing signature. The only reason to believe it existed at all is that its prior existence would make the numbers add up. The mechanism is this. If early dark energy was real, it injected additional expansion into the universe during those first few 100,000 years. That faster early expansion would have compressed the sound horizon the maximum distance that pressure waves could travel through the primordial plasma, before the universe cooled and froze those waves in place. A smaller sound horizon means that when you run the CMB data backward through the physics equations to calculate the current expansion rate, the answer that comes out is higher, closer to 73. The blueprint, read with early dark energy written into it, would no longer say 67.4. It would say something closer to what the distance ladder has been insisting for years. The proposal came from Mark Kamiankowski at Johns Hopkins University and Vivian Poulin, published in 2019. The cosmology community took it seriously immediately, not because it was proven, but because it was the most mathematically coherent attempt anyone had produced to bridge the gap without requiring a complete reconstruction of the Standard Model from scratch. It spread through conferences and preprint servers with the velocity of an idea that people desperately want to work. But early dark energy has a problem, a serious one. It patches the Hubble tension, and in doing so, it tears open the S8 tension. The S8 tension is a separate crisis, running in parallel a disagreement about how clumped and concentrated the matter in the universe actually is. The CMB data from Planck predicts a specific level of structure, how tightly matter should be bunched into clusters and filaments across cosmic scales. Modern galaxy surveys, KIDS, DES, surveys that physically map hundreds of millions of galaxies across the sky, consistently measure a universe that is smoother than Planck predicts. Less clumped, more spread out. The Standard Model says matter should be arranged a certain way. The universe, when you look at it directly, is arranged differently. Early dark energy makes this worse. The same mechanism that compresses the sound horizon and pushes the Hubble constant upward also affects the growth of cosmic structure in ways that amplify the S8 disagreement. You pull one thread to close the hole, two new tears open along the seams on either side. This is what it looks like when a patch doesn't fit you. Take a piece of fabric to cover a hole in your coat, but the tension of the new material pulls at the old stitching around it, and two more seams split open that weren't torn before. And yet, and this is the part that should make you stop and sit with the discomfort, there is not a single piece of direct observational evidence that early dark energy exists. Not one. No telescope has detected it. No particle experiment has identified it. No measurement has returned a signal that requires it to be real. It is a mathematical construct, engineered backward from a contradiction. The researchers did not observe something strange and conclude early dark energy must be responsible. They observed a disagreement between two numbers and designed an entity whose existence would make that disagreement disappear. Would you accept a solution designed to fit the data rather than discovered from it? In normal science, when someone proposes an invisible entity that existed briefly, left no direct evidence, and is invoked solely to explain why other measurements don't match, that gets a cold reception. In philosophy of science, the move has a name, and it is not a compliment. But early dark energy is not being dismissed. It is being actively modeled, tested against indirect constraints, refined by serious researchers at serious institutions. Because in cosmology in 2024, this is the best available solution. Early dark energy is, essentially, physicists saying something happened, then it disappeared. Nobody saw it, it left no direct evidence, but it explains why our numbers don't match. In ordinary science, that is called a fallacy. In cosmology right now, that is called the most promising hypothesis on the table. That is the state of the field, not because physicists have given up on rigor, because the universe has, so far, refused to offer anything better. But while theorists are trying to patch the standard model from the inside, JWST has been turning its mirrors toward the very first galaxies that ever existed. And what it sees does not merely challenge the model, it comes close to declaring the model impossible. According to the standard model, the early universe had to be a simple place. Chaotic, yes. Violent, certainly. But structurally simple, unformed, undifferentiated. A kitchen after a gas explosion, with matter scattered in every direction and nothing yet assembled into anything recognizable. Structure was supposed to come later, much later. The standard model is very specific about this. It has a timeline. It has physics behind that timeline. And the timeline says that what James Webb found cannot be there. James Webb looked, and it saw skyscrapers already finished, down to the last detail. Galaxy GN-Z11 exists at a distance corresponding to when the universe was just 430 million years old, 3% of its current age. 3%. At that point in cosmic history, the standard model allows for early, small, irregular proto-galaxies, rough sketches of structure still assembling themselves from the raw material of the Big Bang. GN-Z11 is not that. It already contains billions of stars. Its core blazes with a luminosity many times greater than predictions allow for an object of its age. Hubble had glimpsed it before and flagged it as anomalous. James Webb confirmed every anomalous feature and sharpened them into clarity that removed any remaining ambiguity. This galaxy is real, its properties are real, and it should not exist. In 2023, Mike Boylan-Colchin at the University of Texas published an analysis of the early galaxies James Webb had been finding across the sky. The conclusion was stark. These galaxies carry stellar masses between 10 and 100 times larger than the theoretical maximum the standard model permits at their observed ages. Not slightly over the predicted range, not nudging the boundary. Between 10 and 100 times beyond the limit. The kind of discrepancy that does not get absorbed into error bars or explained away by a revised calibration. The reason this is physically impossible under the standard model is not arbitrary. It comes directly from the model's description of how structure forms. Dark matter, cold, slow, invisible, needs time to gravitationally collapse into what physicists call dark matter halos. The dense scaffolding that gas then falls into, cools inside, and eventually forms stars within. That collapse is not instantaneous. It proceeds hierarchically. Small halos form first, merge into larger ones, which merge into larger ones still. Gas accumulates, stars ignite, galaxies grow. The entire sequence has a minimum timescale set by the physics of gravity and the initial density fluctuations in the early universe. You cannot skip steps. Gravity does not allow shortcuts. The standard model says that process needs billions of years to produce galaxies of the mass and brightness that James Webb is finding. James Webb is finding them after a few 100 million years. It is like arriving at a construction site on day 3 of a 5-year project and finding a finished 50-story building, fully furnished, with people living in it, while the architectural plans still show the foundation crew working on the basement. GN-Z11 is not alone. Cosmic Vine, a massive filamentary structure of linked galaxies, appeared far earlier than models predict. Large-scale organization of that kind could exist. El Gordo, a colossal galaxy cluster whose mass and collision dynamics require an implausible density of matter in the early universe, was already a problem before Webb and has become more of one since. These are not isolated anomalies. They are a pattern, a repeating, persistent pattern of structures that are too large, too organized, and too old in the wrong direction, assembled too early for the standard model's timeline to accommodate. The scientific community has not reached consensus on what this means. Some researchers argue that star formation efficiency in the early universe was simply much higher than models assumed, that gas collapsed into stars faster, that feedback mechanisms suppress star formation less effectively, that the process ran hotter and quicker than the standard model simulations captured. This interpretation saves the framework by adjusting one of its parameters. Others find that adjustment insufficient. The discrepancy is too large, too consistent across too many independent observations to be absorbed by a single tweak to star formation efficiency. They argue that the dark matter model itself needs revisiting, that cold dark matter's behavior in the early universe was different from what lambda CDM encodes, and that without changing the underlying description of what dark matter is and how it behaves, no amount of parameter adjustment will close the gap. If the universe can build massive structures far faster than the physical limits allow, what does that say about the limits themselves? Cosmologists are feeling exactly like an archaeologist who just unearthed a fully functional smartphone in a Neanderthal burial site. Not excited, not intrigued, unsettled in the specific way that comes from knowing that the thing you are looking at should not be there, and that its presence means something you built your entire career on top of is wrong in a way you have not yet figured out how to fix. And if the early galaxies are challenging the timeline, then the structure of the universe itself is challenging the mass budget. Because the thing supposedly holding all of this together, the invisible scaffolding that every galaxy, including our own, is built inside of, is not behaving the way we thought. And the James Webb findings are only making that problem harder to ignore. 27% of the universe is made of something invisible. It does not emit light. It does not reflect light. It does not interact with electromagnetic radiation in any form that any instrument humanity has ever built can directly detect. Its only relationship with the observable world is gravitational. It pulls, and things respond to that pull. And the entire existence of galaxies, including the Milky Way, including every star you have ever looked at in the night sky, depends on it being there. Without it, galaxies do not hold together. Stars scatter. Structure dissolves. The universe as we know it simply does not form. The problem is that our model of this thing, the model that underpins every cosmological calculation of the last 30 years, is wrong in a way that James Webb has now made impossible to ignore. Cold dark matter is the CDM in lambda CDM. Cold meaning slow-moving at the time of the early universe, as opposed to relativistic particles that would have streamed too fast to clump together gravitationally. The model predicts that cold dark matter aggregates. Hierarchically, small clumps form first, pulled together by gravity. Then those clumps merge into larger ones, which merge into larger ones still, building upward in scale like a slow cosmic construction project, proceeding from bricks to walls to buildings to cities. Galaxies form inside these dark matter halos, their gas cooling and collapsing into stars within the gravitational wells the dark matter has already dug. The model is specific, mathematical, and has been tested against observations for decades with considerable success. but it is failing now in two directions simultaneously. The S8 parameter measures how clumped and concentrated matter is across the universe, how tightly packed the cosmic web of filaments and voids actually is at large scales. The CMB data from Planck predicts a specific value for S8, a specific level of structure that cold dark matter's hierarchical assembly should have produced by the present day. Modern galaxy surveys, KIDS, the Kilo Degree Survey, and DES, the Dark Energy Survey, have mapped hundreds of millions of galaxies across enormous swaths of sky and measured the actual distribution of matter directly. What they find is a universe that is smoother than Planck predicts, less concentrated, more spread out, fewer small galaxy clusters than the model expects, fewer satellite galaxies orbiting around large galaxies like our own than cold dark matter simulations consistently produce. The real universe, at the scales we can now measure with precision, is less structured than the model says it should be. Cold dark matter predicts a universe wound tighter. The universe we actually live in is looser. Now hold that thought alongside what James Webb found in the previous chapter. Galaxies in the early universe that are too massive, too bright, too fully assembled for the standard model's timeline. Too much structure, too soon. And here, in the present-day universe, not enough structure. The two problems point in opposite directions. The early universe was overstructured. The late universe is understructured. Both contradict cold dark matter. Both cannot be explained by the same simple parameter adjustment. They pull against each other, and the thing caught in the middle, the thing that has to somehow account for both anomalies simultaneously, is the cold dark matter model itself. Cold dark matter is like a musical score with every note precisely written. But when the orchestra actually plays it, the first movement runs faster than written, and the final movement runs slower. And no single adjustment to the tempo marking fixes both problems at once. The field is not standing still. 3 alternative frameworks are actively being developed, each proposing a different modification to what dark matter actually is. Fuzzy dark matter replaces the heavy, slow particles of cold dark matter with an ultra-light particle so featherweight that it behaves quantum mechanically at astronomical scales. Its wave nature suppresses the formation of very small structures, which would explain why we see fewer small satellite galaxies than cold dark matter predicts, without abandoning dark matter altogether. Warm dark matter proposes particles that were faster moving in the early universe than cold dark matter assumes, which similarly smooths out small-scale structure in ways that better match the galaxy surveys. Self-interacting dark matter goes further still, proposing that dark matter particles do interact with each other, not electromagnetically, but through some unknown force which changes the density profiles of dark matter halos in ways that affect both galaxy formation and large-scale structure simultaneously. All 3 are still hypotheses. None has been confirmed. All are being tested against data with increasing urgency. If 27% of the universe is not behaving the way we think it does, how much of what exists do we actually understand? Dark matter is the only thing in physics whose existence we are confident about, entirely because of what it does to other things, never from observing it directly. Every piece of evidence for dark matter is inferential galaxy rotation curves that don't match the visible mass, gravitational lensing that bends light more than visible matter can account for, the large-scale structure of the cosmic web that could not have formed without an invisible scaffolding holding it together. We have never seen dark matter. We have only ever seen its shadow on everything else. This is, in the most literal sense, how physicists prove there is a ghost in the house. I cannot see it, but that chair just moved by itself. Something is there. The chair keeps moving. We keep inferring the ghost, and now the ghost is not behaving the way our ghost behavior model predicted, and we are not sure whether we have the wrong model of ghosts or whether there is something else entirely moving the furniture. But this is the most important thing you need to hear right now. All of these crises, all of these contradictions, all of these places where the map disagrees with the territory are not signs that science is dying. They are signs of something far more extraordinary than that. Every time in the history of science, when a great model met a crisis it could not resolve, what came next was not collapse, it was revolution. This is not optimism. It is the historical record, repeated with enough consistency to qualify as a pattern. At the end of the 19th century, Newtonian mechanics stood as the most complete and successful scientific framework ever constructed. It had explained the motion of planets, the behavior of falling objects, the mechanics of machines, the tides of oceans. Lord Kelvin, one of the most decorated physicists of the era, declared in 1899 that physics was essentially finished. The great work was done. What remained were details, refinements, decimal places. He acknowledged two small remaining problems, two areas where the data didn't quite fit, two things the model hadn't yet fully explained. He called them two small clouds on the otherwise clear horizon of physics. Those two small clouds were the failure of the Michelson-Morley experiment to detect the luminiferous ether and the inability of classical mechanics to explain black-body radiation. The first cloud became the special theory of relativity. The second became quantum mechanics. The two greatest scientific revolutions in human history both grew directly out of the anomalies that the most confident minds of their era dismissed as minor inconveniences. The second precedent is closer and more personal to this story. In 1998, Adam Rees and his collaborators were measuring the expansion rate of the universe using Type 1a supernovae, expecting to measure how much gravity was slowing the expansion down. What they found instead was that the expansion was not slowing, it was accelerating. The universe was not coasting, it was being pushed by something. Something with no name, no theoretical precedent, no place in any existing model of the cosmos. The discovery contradicted every cosmological framework that existed at the time. It forced the complete restructuring of the standard model to include lambda dark energy, a term representing an unknown repulsive force that fills all of space. It rewrote modern cosmology entirely. And it won Rees the Nobel Prize in 2011. One anomaly, pursued rigorously, produced the most significant revision to our picture of the universe in a generation. What the Hubble tension is doing now is the same kind of forcing function, applied at the same depth. It is compelling physicists to consider possibilities that were previously not on the table among them. The genuinely radical idea that the physics governing the early universe and the physics governing the universe today may not be exactly the same. That the laws, or at least some of the constants embedded in those laws, may have evolved. Modified gravity theories propose that Einstein's general relativity, near perfect as it has proven to be, requires corrections at cosmological scales that reveal themselves only when you measure the universe precisely enough. Dynamic dark energy models propose that the cosmological constant lambda is not actually constant, that dark energy has been changing in strength over cosmic time, and that its current value and its early universe value are not the same. Inhomogeneous universe models propose that the assumption of large-scale uniformity, the cosmological principle, that the universe looks the same from every location, is simply not accurate at the scales we are now capable of measuring, and that the universe has structure on scales large enough to affect the expansion rate we observe from our particular location within it. None of these is confirmed. All of them are being pursued, tested, constrained by incoming data from instruments that did not exist 5 years ago. The ESA's Euclid telescope, launched in 2023, is currently mapping more than 1 billion galaxies across the sky with a precision designed specifically to measure both S8 and H0 with enough accuracy to distinguish between competing models. Its full dataset is expected between 2025 and 2030. The Vera C. Rubin Observatory in Chile, running the legacy survey of space and time, will photograph the entire accessible sky every 3 nights for 10 consecutive years, accumulating a dataset large enough to test every alternative model currently on the table and several that haven't been proposed yet. 10 years of full sky imaging, 3 nights per cycle, for a decade. The volume of data it will produce has no precedent in the history of observational astronomy. This is not a map being torn up, it is a map being redrawn at 1,000 times the precision of the previous one, because we finally have the instruments to see where the old map was wrong. The old map was not worthless. It got us here. It built the entire framework of modern cosmology. But it was drawn with tools that could not resolve what the territory actually looks like at this level of detail. And now that we can see more clearly, the discrepancies are not embarrassing failures. They are coordinates. They are telling us exactly where the new map needs to be different from the old one. If you knew that the answer to the largest open question in cosmology would be found within 10 to 20 years, would you feel that you are living through a historical moment? The physicists working on this right now are in the position of the people who saw a computer screen for the first time. They know something enormous is coming. They can feel the shape of it in the data, in the tensions, in the places where the model strains against what the universe actually shows them. They just don't yet know exactly what it looks like. This is the story of the edge of human knowledge, and of what happens when we are brave enough to stand at that edge and look directly into the dark. Everything told in this story, the Hubble tension, the impossible galaxies, the misbehaving dark matter, the decade of irreconcilable measurements rested on an assumption so fundamental it was never stated out loud. An assumption so deeply embedded in the methodology that questioning it felt, for a long time, like questioning mathematics itself. The assumption is this: we are typical. Our location in the universe is ordinary. The patch of cosmos we inhabit is a representative sample of the whole. When we measure the expansion rate of the universe from here, we are measuring the expansion rate of the universe, not the expansion rate of some anomalous, unrepresentative corner of it. What if that assumption is wrong? In 2023 and 2024, a series of independent studies, including data from the Euclid telescope and analysis from the Dark Energy Spectroscopic Instrument, known as DESI, began converging on something that had been whispered about for years, but never confirmed with sufficient precision. The Milky Way and our local group of galaxies may be sitting inside a region of space that is significantly less dense than the cosmic average. A vast underdensity, a bubble, hundreds of millions of light-years across, where matter is thinner on the ground than it is in the universe at large. Cosmologists have names for it: the local void, the Hubble bubble, a region so large that for most of human history, we had no instruments capable of detecting that we were inside it. If this is real, and the evidence is not yet conclusive, but it is accumulating, then everything that follows from it reshapes the entire debate. A region of space that is less dense than average expands faster than average. That is straightforward gravitational physics. Less matter means less gravitational braking on the local expansion. So if we are inside an underdense bubble, the expansion rate measured from our position would naturally appear higher than the true global average, not because our instruments are wrong, not because the physics is broken, but because we are not in a typical place. We are standing in a room that is expanding faster than most rooms, and we have been assuming all along that our room is average. The number 73 would not be a crisis. It would be a local measurement accurate for where we are standing that we have been mistakenly treating as universal. The number 67.4 from the CMB would not be in contradiction with it. It would be the actual global average, read from light that traveled across the whole universe before arriving here, averaging over regions dense and sparse alike. Two scientists arguing about the average temperature of Earth, one measuring in Hawaii, one using global satellite data, both correct. Neither recognizing that Hawaii is not representative of the whole planet. The implications of this are not small. If our position in the universe has been biasing every local measurement we have made for a century quietly, invisibly, in a way that no one recognized because no one had instruments sensitive enough to see the bubble's edge, then the decade-long argument at the heart of modern cosmology may not be about a flaw in the physics. It may be about a flaw in the assumption of where we are standing when we do the physics. And that opens a question that does not close easily. If our location has been distorting our measurements in one direction for 100 years of cosmology, how many other things in physics are being distorted by our position in ways we have not yet thought to check? Adam Rees warned us that something is wrong with our universe, or with our understanding of it. It turns out, both are true. The universe is doing something we did not predict, and we have been watching it from a vantage point we did not know was skewed. The real question was never how fast the universe is expanding. The real question is where we are standing inside it, and whether we will ever find a vantage point neutral enough to see the whole picture clearly.